Okay, so the outline is the start off is just something that should be familiar to many people, and just a brief mention of what Helmholtz did on vortex dynamics and the reference to potentials. And then I'll move on to consider what is considered the real beginning of topology. Riemann's paper, almost same time of Helmholtz's work of 1858, Riemann's 1857, proposed what we may say a solution to the problem of multivalued functions. And in particular here, I will focus on this word multivalued potentials. Very interesting, the work of Kelvin, as you know, started off with his vortex atom theory that became the beginning of what we may call topological fluid mechanics. Is really the very first topological field theory of our time. And well, I spent quite a bit of time examining the various papers by Kelvin, and in particular, he considered the result of Riemann and wanted to apply the result of Riemann to Green's potential theory. I think this is pretty unknown, and I'm glad to share with you this result. Now I will move to the impact of topology on physics. Has still relevance for multivalued potentials, because the Harnoff bomb effect was meant to be a crucial evidence for the role of potentials in physics, so to in physical reality, so to speak. Then I will move to very recent work done on condensates, in particular defects, and I'll take this so-called hydrodynamic interpretation to keep going on these relationship between potentials and physical effects. And I'll consider very modern technique based on Kleiner's work and application of multivalued gauge theory to defects, and then conclusions. So this is the outline of my talk. I will go very slowly, and of course I try to be rather elementary. So if there are questions, or if you spot inaccuracies in what I say, please do intervene. Okay, we keep it as informal as possible. So let me start with vortices in nature, just to give you an idea of what we are talking about. Well, this is, of course, a tornado in the atmosphere, maybe in Oklahoma, maybe in the Mediterranean coast. And this is a vortex in water. Okay, so these are just two visualization of a mechanism that is making the fluid, either air or water, rotating about, say, a center. This center can be a center of low pressure, something like this. Now, of course, the region of intense rotation is more or less where you see localized these dust or these bubbled water, and the region of weak rotation is very even very near, but anyway away from this intense region of vorticity of rotation. Now Helmholtz, as I said, was the first to tackle the problem that you will recognize in a moment. He envisaged that the two important aspects were missing in the theory of fluid motion. One was the very important aspect of viscosity, and the other one was the aspect of concentrated vorticity. So here you have what we may say, the first approach of Helmholtz, first of all, to distinguish, imagine to take a cross section, to distinguish a region of irrotational flow from a region of rotational flow. And then you just go on with your mathematical idealization, and you say, okay, where there is irrotational fluid, I take it as an ideal irrotational fluid. In other words, no viscosity at all. And where there is the region of rotation, I considered localized vorticities. So it's just an abrupt change of mathematical specification, if you like, on the boundary of this blob of vorticity. Well, Helmholtz derived his conservation laws for vortex dynamics in 3D, in 3D. And here I won't mention these laws, but I'd like to put in context the three-dimensional context of what we saw before. So imagine that we have an infinite domain represented by this box, and these blue color represent a fluid that is homogeneous, incompressible, and inviscid. And then we take a velocity field function of a vector position x, and we assume, because of incompressibility, divergence equals 0, and eventually the velocity going to 0 at infinity. Now the blob of vorticity becomes a tube in this context. So you have a region where vorticity is exactly 0. And so you have the condition that you can express this as velocity given in terms of a potential, phi. And evidently, if u is given by grad phi, you will have curl of grad u of grad phi equal 0. It means that we have indeed a potential that is well defined around that. And the region where you may think is localized the vorticity, the curl of u is different from 0, and there you don't have a potential. You find these few comments that I just made exactly on the front page, or second page, if you like, of his original paper, of Helmholtz's original paper, where indeed he says, well, I leave to others the problem of viscosity, and I will tackle the problem of concentrated vorticity. He goes on, and as we know, he derives the conservation laws of vortex dynamics. Now we have a circulation because evidently the curl is different from 0, and you remember from Stokes' theorem, you have a circulation of the velocity around a loop, C0, and I call it gamma, and I put this suffix of C0 just to denote that I refer to any loop that is embracing this tube of vorticity. And as you know, Stokes is just reported there. R0 is just the cross section. Now, as you see, I put down a diagram of the velocity, how the velocity goes with respect to the radius, radial distance from the center. And you see it goes from a certain value just down 0 as we go to infinity. The certain value that is given there is just reached when we have a finite cross section R0. Otherwise, evidently 1 over R makes us believe that the velocity would eventually go to infinity. We would have a singularity. Of course, that is not realistic. And that was part of the concern of Helmholtz. Okay, so with Riemann, the paper of Helmholtz was influenced by Riemann. They were not far away one another, and Riemann, as you know, took then the chair of Gauss, and Riemann was not a pupil of Gauss, technically speaking, some historians wrongly report, Riemann was just applying for the chair, and Gauss was president of the commission. And of course, we know that he was in favor of, very much in favor of Riemann. Gauss himself was very keen on topology. Well, Riemann's work started from thesis, was not really about what we could say topology, was actually about the analysis of functions of complex variables. And as for a trigonometric function, we know that this function may have multiple values, like the log of z, if z is a complex variable. Here, I want to finalize his work to the context of, say, potential theory. So let's say, as he did, assume the existence of a scalar function, and for the moment, consider that we are in the plane, okay? So in the plane, phi is a function of x and y, and we take this function, in modern word, we would say as an exact differential. In other words, we can write the function in the form you see, where the functions a and b, functions of x and y, are defined through the partial derivatives of phi in terms of x and y. Okay, so by just direct computation from a and b, you can show that dB dx is equal to dA dy. In other words, dB dx minus dA dy is equal to 0. And if you consider a loop, for example, a curve in yellow as you see, C0, and you consider the integral over this loop of this differential d phi, a dx plus b dy, you discover by direct integration, in other words, by calculus, that this is 0. Some of you, of course, recognize the difference between the gradients b and a as a contribution, a component, if you like, of the curl operator. Anyway, if this is 0, it means that for exact forms, we can establish that the circulation over a closed curve, over a loop, is 0. And no matter how is drawn this loop on the plane, even a point would do. And indeed, we say that for any loop C, the circulation is 0, and the loop can be shrunk to a point. In this fashion, we say that the region is simply connected. Of course, if it is simply connected, you learn from first year courses that not only you have a potential well-defined phi, but we can reverse one of the strands, this loop, and reversing the orientation, we can go from a point P to a point Q, and we just consider the difference between the value of the function phi at P and the value of function phi at Q by the gradient theorem. Okay, now suppose there is an obstruction. No wonder why I chosen this obstruction as a red spot, just reminiscent to the red spot given by vorticity. Okay, suppose there is an obstruction. So Riemann says, then what we do? Well, evidently we have two different types of loops. One loop, C1, that can be shrunk to a point, and one loop, C0, that prevents, that cannot be shrunk to a point because the obstruction prevents this mechanism. And we say that the region is now doubly connected. Okay, so if there is an obstruction, or if you like, a hole in the region, then we say that the region is doubly connected. All right, so the idea of Riemann's paper 57 is to insert a cut. We'll call it Q, and so we can reduce a doubly connected region to a simply connected region. And remember, this cut may have two parts, one side, the positive side, and the negative side. And this allows us to see really the opening up of this new region. Okay, so this can be immediately transferred to some of the functions that we are familiar with. For example, the arctan function or any other trigonometric function. Well, the arctan function, as you see in the plot, has, of course, values theta periodically repeated by 2 pi. So it's a mod 2 pi function. And what we do in first year courses, we just ask students to restrict the domain of definition of our sine, cosine, tangent, etc., inverse tangents, inverse functions, just to focus on the values of the function on a given period. Well, the use of cuts can then reduce a multi-valued function to a single valued function, because if we reduce to 2 pi any of these trigonometric functions, then evidently we can, for example, consider the inverse of these functions, etc., etc. Okay, now we apply this cut of Riemann in a more general sense to a surface, for example, and the cut that was visualized by a segment now becomes a surface in green with the letter sigma. And if the region we consider is bounded, so it is limited with a boundary C, then the remarkable thing that was kind of left out in Riemann's discussion is that the boundary it gets modified. So the new boundary of the region, of the bounded region R, is now the previous piece of boundary C plus the positive and negative parts of the cut. So this is the theorem of Riemann, in more or less in his words, an n+1 ply connected surface now S is changed into an n ply connected surface as 0 by the insertion of a cut of surface sigma that does not disconnect S. Okay, now we leave Riemann's behind and we move to Kelvin. Well, you see, it passed, well, more or less 10 years passed from Riemann's work and Helmholtz's work. And in 1867, William Thomson became aware through his good friend Tate, much younger than him, at the time in Edinburgh. He became aware of Helmholtz's work. He asked for a translation, and the conservation laws of Helmholtz inspired immediately Lord Kelvin, who was in search of a general theory of everything, we would say now, inspired Kelvin to develop his vortex atom theory. Bottom line of this vortex atom theory was to quantize energy by means of topology. That was really, really a remarkable thought he had at the time. And this is one of the drawings that were published on vortex motion paper of '69. But he asked Tate to translate Helmholtz for himself into English. Tate could read German, and he provided a translation, and Kelvin was so taken by the depth of the results of Helmholtz to push Tate to publish the translation to English. And now we have actually more than one translation, the first one, of course, due to Tate. So it took more or less 10 years, but as soon as Kelvin realized that, he saw the implications of the work of Helmholtz, and because Helmholtz, in a little note, pointed out to the problem of multi-valued potentials in a possibly complex, topologically complex domain, then Kelvin picked it up immediately. So imagine what we had, what Kelvin had in mind was, imagine a space, maybe a microcosm, maybe a molecule at the molecular scale, space filled by ether, idealized the fluid, envisaged, full by vortices. Is really reminiscent of what we can see now by watching the simulations of Carlo Berenghi in superfluid helium. Well, we have these vortices there, and then he made a step farther. Of course, immediately conjectured the number of results that have proven to be either too difficult to be proven mathematically rigorously, or even wrong. For example, stability of these vortices in this ether. And one of the aspects he immediately pondered on was, what about if we consider this fluid as a Gruyere cheese, we would say, as a region of space filled by empty tubes. We remove vorticity and we would have these empty tubes there. So clearly that poses a question for him about potentials, because as I said, Helmholtz immediately pointed out that in a space that is multiply connected, then the potential is not well defined. And here we are with Kelvin's example. You can find this really in his 1869 paper, and is a pretty long story. So you will see in 2 slides really a recap of what he did, and more or less modern notation, of course. And it took me days to understand what he had in mind, also because of different ways we use symbols. Anyway, here we have in this cyan color, in this light blue color, the fluid, the ether, and one of these empty tubes visualized there. So now this central little tube is a hole in the region. And the region immediately think of it infinitely extended, or if it is finitely extended, better now, we think of it with a volume given V, and of course a boundary given by the letter S. Okay, what we do with this? Well, Kelvin wanted to put at work the idea of Riemann. And so he said, well, let's consider a kinetic potential that has the form exactly as the function you saw before, arctan. Arctan, and you immediately think that because of the symmetry chosen in the picture, you can think of this as a function of 2 variables only, x and y. So this function is multi-valued. Okay, and you work out the velocity, so you just work out the gradients, and you find that indeed you have a well-defined velocity, and this velocity is actually solenoidal and irrotational. So you just do your computation. All right, now you look at potential theory, and on this I should say that Kelvin was really one of the very, very first to have in his hands the work of Green. Green, as you know, published, so to speak, printed a number of few copies of his work, and one of the copy was given to Kelvin through Tate. And Kelvin, at the very time he received this copy, had planned to visit Fourier, because was keen on understanding what we may say now, something like a statistical mechanics approach to heat. And he was so taken by the copy of Green's that when he arrived in Paris, he spent all his time in Paris talking to Fourier about the Green's work on potential. Anyway, this is the first identity of Green, and you can read this as an extension, if you like, of the divergence theorem, of the Stokes theorem. All these versions can be related one another. So you have an integral, a volume integral related to a surface integral, and phi and psi are two scalar potentials. I won't say much at the moment on this, just focusing on the fact that V is the volume of our, say, blue region here, and S is the boundary of this region here. All right, now let me rewrite this expression in this form. So I just take this term on the other side, and I can also rewrite the same expression in this alternative form. Just equivalent, of course. It's just switching phi and psi, nothing else. Okay, so these are just the two forms of Green's identity. Now, if phi is multi-valued, then, okay, by using this expression here, we can work out this scalar product, and we can prove that this scalar product, whatever is phi, goes to 0. Moreover, again, by using this expression, we can work out the Laplacian of psi. Remember that U is a solenoidal, and so if you take the div of the grad of psi, this is a Laplace equation 2, 0. So psi is harmonic in this volume W. And then by using cylindrical polar coordinates, you can prove that also this quantity is 0, and this quantity is just the product, the integral, surface integral of phi times the directional gradient of psi along the normal direction nu to the surface of W. And this is also 0, as I said. So all this is okay, is satisfied. But what about the alternative expression for Green's first identity? If phi is single valued, of course, if phi is multi-valued, you see this is the gradient of a multi-valued function is okay, and these are all zeros. But what about if phi is multi-valued, is single valued? If phi is single valued, well, this term is 0 because the grad of psi is 0. Okay, so we use that one. But then if phi is a single valued and psi is multi-valued, then this is no longer 0, because we didn't specify phi at all. So if we just substitute the arctan here, we have this expression in general. Now, we want to work out this expression in terms of Riemann's cuts. And this is exactly what Kelvin did. Okay, so if we use Riemann's approach, let me go to this slide. You see immediately that the segment as a cut Q becomes a surface, a green surface that I identified with the letter sigma. And now the new volume is now reduced to singly connected region. Let's restore simple connectivity by inserting the cut surface sigma, and we have a new boundary now. The new boundary is given by the two sides of this green sheet. One side is a sigma minus, the other side is a sigma plus, exactly as we did for the cut Q. Okay, we go back. Remember, I'm just going back with these slides. The emphasis is now on this term, on the surface integral, because the surface integral has now to be redone in terms of the new surface S prime that includes the two sides, the two faces of this sigma cut. One part is this one, and the other part is working out the arctan on the surface on one side. On the other, we have the contribution 2 pi, multiplying this quantity. One quantity sigma minus is 0, one quantity sigma plus is 2 pi. So we have the sum of these two quantities, and by computation, we can prove that the sum of all these quantities is indeed 0, as required for a singly connected region. Well, these 2 pi that you see here, these 2 pi can be interpreted using the words of Kelvin as a circulatory constant, and this sigma, using again the words of Kelvin, as a circulation stopping barrier, It took me years, well, certainly a few days, to think what he meant by a circulation stopping barrier. I couldn't see it until finally I understood that he meant a Riemann's cut. Okay, so by this we can put in a lemma the word of Kelvin. For a multiply connected region with n holes of volume V and boundary surface S, Green's first identity is given by this form, where you recognize the first part is just the original Green's identity, and this correction. You see, he generalizes what he learns from practice, from working out an example. And he says, well, given a number of holes, n, we just insert a number of cuts of surface, each of surface sigma I, and each with an appropriate circulatory constant Ki, to use the word of Kelvin. Right, so we now have a way to amend potential theory for a number of situations.
So may I ask you something?
Yeah, sure. Sure, Anwar, go ahead.
How come that instead of 2 pi, you get some numbers kappa I? How 2 pi becomes different from 2 pi here?
Well, 2 pi represent really the circulation around the hole, and he just gave the name kappa as he used it for circulation in his papers. That's all. 2 pi, remember, 2 pi is the result, is not explicited here, is just the result of integration over sigma minus and integration over sigma plus around the hole.
It's for specific psi that you get 2 pi. Clear. Thank you.
Okay.
Right? Thank you.
Right. So we are now more or less a bit over half of my time. And I want to tell you something about a very important result. This is the Harnoff bomb effect. And for those of you who don't know anything about it, I'll just show it in a couple of slides. Consider a current carrying long solenoid. So it's just copper, if you like, and empty space everywhere else. So by a cube again, or a parallelepiped, I mean an infinite volume, okay? And then you just put your current in the solenoid, and you if the solenoid is very long, doesn't need to be infinitely long. We can't do that, but well, in experiments, a meter long is enough to constrain the induced magnetic field inside the solenoid. So the magnetic field is totally confined inside for a good portion of your solenoid. We know that div B is 0, so eventually these field lines would close up somewhere far away, so that particles around the solenoid are not disturbed by the field. Now we can put our color, red color, to represent the magnetic field, and again A to represent the vector potential, B equals 0 outside. So in steady conditions, in absence of time, we see this analogy between vorticity, curl of U, and the magnetic field's curl of A, U grad phi, and here we have an A grad of a potential associated with the electric field, and then phi equal to 0, where phi E is equal to 0, in other words, where there is empty space. If we consider a loop surrounding this localized tube of magnetic fields, then evidently we have again a circulation that is different from 0 by Stokes. And we can now follow what Harnoff and Bohm proposed in 1959. They proposed the following experiment. You just confine your magnetic fields in a way that is represented in the picture. B is totally 0 outside this tube, and then you just create a flow of electrons going around one side, the other, etc. And then you put an interference device to measure this flow of electron passing by the field, the magnetic field different from 0. Remember that the electrons are traveling in a space where B is different, is equal to 0, okay? So there is no action of B in the flow of electrons. Now, it took a long time to prove these, and I myself, when I was young, ran into a couple of groups of people attempting to prove experimentally these. And finally, a group of Japanese proved the Harnoff-Bohm effect. So this is just a pictorial representation of what I just explained before. This picture is taken by a Physics Today paper of some time ago, written by Tonomura. Tonomura was lead of this group. You measure, in actual fact, you measure a dislocation of the electron isophase fronts. And the dislocation, this is the picture published in a PRL 1986 by the Tonomura group. And it proves that indeed the potential has an effect on the empty space outside the solenoid. And these effects can be measured by a difference in phase, and the jump in phase is given by the circulation and these constants, Planck constant divided by the electron unit charge. Let me stress again, because of the analogy that I pointed out, that the potential as the velocity goes like 1 over r. If r approaches the 0 line of B, then evidently we have an infinity. But again, here we have a finite flux tube. So the singularity, the apparent singularity associated with A, once again, is avoided. Okay, we come to modern times and the discovery of condensates. And first achievements of condensates was awarded a Nobel Prize to with a Nobel Prize to Cornell, Kettle, and Riemann. Of course, the words Bose and Einstein mean that this condensation state of matter was previewed by Bose, an Indian physicist who sent a letter to Einstein, and Einstein was so taken by the letter of Bose that he decided to translate the letter into English and publish the letter in the I think the Annals of Physics, the Annalen der Physik decision, without consulting Bose. Of course, he let Bose know about this decision. The letter was published. And so we call it a Bose-Einstein condensed state of matter, as a state of matter that is reached when particles like bosons are brought to a temperature of millikelvin, temperature even lower than that, and the condensate becomes controlled, so to speak, by a single wave function, which is more or less representing the minimum energy state of the system. Because of this, soon afterwards, people looked for strange lack of particles that we may call defects, and the role of topological phases of matter in this condensed state. And the work was awarded by another Nobel Prize, Paulus, Haldane, and Kosterlitz in 2016. Well, I mentioned defects, I mentioned the ground state energy, and that led immediately at the time of Bose, Bohm in particular, and Madlung in particular, the two in the 2730s, in those years, to provide a hydrodynamic interpretation of this particular state of matter. And the reason is very interesting, is the fact that they were not very happy about the quantum mechanics developments of the time, and they wanted to propose a continuum deterministic description of nature by resorting to hydrodynamics. Well, you find a very beautiful description of all this in a book by Viat, a book published in 2005. Anyway, in the hydrodynamic interpretation, you have, of course, to deal with the phases. These phases are associated with the wave function, the fundamental wave function associated with the nonlinear Schrödinger equation that governs, so to speak, the background wave function of the system. So the phase, we call the phase chi in this case, and the hydrodynamic interpretation of the phase allows us to identify grad of chi as a velocity of a virtual fluid. Remember, it's not really a fluid, it's a gas of particles that low temperature, but we can describe rather well these gas of particles in terms of dynamics by considering hydrodynamic dynamics of these virtual fluid. So we have a U. I put a tilde here because it doesn't scale correctly with grad chi, and chi is just you can consider it as a kinetic potential. Well, in this case, I said they may form defects. In other words, really holes in the condensates. And these defects have been seen, and the defect is just, as I said, a hole in a condensate where there is no mass at all, no particles, okay? All right, so in this, if this is a hole, we can think of this actually as a nodal line of the background wave function, and so we can focus on this nodal line. I'll keep visualize this as a little very thin cylinder just to keep track of this nodal line. And indeed, we can think of vorticity now as a delta, as a Dirac delta function. So we identify a defect with a vortex line in a mathematical sense. It's just a Dirac delta function. Well, the ambient space is filled by, of course, isophase surfaces S of the wave function chi, where chi is a constant in value. So you may think of what is called mathematically the open book decomposition of the ambient space. So you think of your infinite space foliated by these isophase surfaces as the pages of a book. They are all hinged on this nodal line. And because U tilde is grad chi, then the velocity is just the normal to this surface. So you see again that if you go round the nodal line, you will go round with the velocity. So evidently, you may think that there is a circulation. Indeed, chi is multivalued. and there is circulation. The fact now is that this velocity can go to infinity because it is a nodal line, is no longer a vortex finite tube. So this puzzles people. And the problem is evidenced by the fact that the curl of u being grad chi, is 0. So there is zero rotation around the nodal line, but along the nodal line, because of a Dirac delta distribution of vorticity, there is vorticity. Now people get along with this with no much, not too many problems, but technically speaking, this poses a problem. And mathematically, this problem was challenged and solved by Kleiner. Well, Kleiner developed multi-valued theory. Kleiner is very, very old now and also ill, unfortunately, but Kleiner was a student of Feynman and worked with Feynman for many, many years. And so he learned a great deal from Feynman, and he published a book on multi-valued functions in physics, in theoretical physics, not long ago. I can't remember the date, but I'll put it in the references. Anyway, Kleiner's technique is just to make use of Riemann's cut and give these cuts a physical sense. So we have a defect cross section in front of us. We have a theta that goes around it. We know that is multi-valued, so we put a cut, again represented by this green segment. And in 3D, we have one of these surfaces as a cut surface. So we identify S with a cut surface sigma. Now, sigma is a locus of a Dirac delta vector distribution. Now things get a bit more difficult here. I'll skip all the details, but in summary, what you find by direct application of Kleiner's theory is a velocity u that is now given by grad chi and the contribution from this Dirac delta distribution. Now, don't get confused by my terminology. I put emphasis on sigma, but grad chi does not depend on sigma, neither delta. So whatever sigma you choose, you get the right u. Indeed, this theory is gauge independent from sigma. And of course, this bold delta just exemplifies, stands for this description of the delta, Dirac delta, just constructed, if you like, on the cut surface sigma. So now we are okay because vorticity is definitely different from 0. Why? Because although the curl of grad is still 0, you can take the curl of this bold delta, and what you find very nicely is that you get a bold delta, a distribution along the nodal line L, which is in actual fact representing the vortex line. Indeed, the bold delta is just delta Dirac along the tangent to the nodal line. Again, we have a constant gamma here in front, and these represent this virtual circulation, if you like, around the nodal line, if you like, crossing the circulation stopping barrier, in words of Kelvin. Conclusions. Well, we have now very interesting recent developments in many fields, application of Kleiner's multivalued gauge theory in distributional analysis to defect theory in various fields, geometric optics, superfluids, condensed matter physics, new materials. We have recent interesting developments in application, not only of Kleiner's multivalued gauge theory, but also, I hope, Kelvin's approach to potential theory to revise or new work on cosmological analog models in black hole theory, in multiverse theory, and string theory. The outcome of this is a kind of the significance I wanted to give to my contribution, and is first of all the realization of importance, I would say, of potential theory in modern physics. I can add of multi-valued potential theory. You know, theoretical physicists and physicists, experimental physicists, even more so, have been extremely reluctant to regard the potential theory as a physical theory. They thought for decades that was just a mathematical tool for mathematicians, but Harnoff put in context the importance of potentials and the importance of topology in physics. And this gives me a chance to mention progress in topological field theory in all contexts, and mathematical theory of natural phenomena at all scales, of course, from string theory to cosmology, and of course classical field theory as well, and inspiration for the mathematical treatment of singular behavior of physical processes. And we have examples of these without resorting to rather abstract theories. We can just simply think of electric surfaces of discontinuity, or the problem of reconnection in vortex dynamics in fluid flows, where two vortices come to contact one another and come to interact and reconnect by changing topology. As promised, I leave you with a list of references. They're all basically, all these have been quoted except one, which is this, and this is a paper that is coming out hopefully in a couple of months, and is in a book dedicated to knotted fields. So thank you very much for your attention. Thank you.